Hello everyone. Welcome to the another lecture of periodic classification of elements class 11. Myself Suman Singh. So in the last class we have discussed about the modern periodic table. Okay. So now today we will discuss about periodic properties. Okay. So in periodic properties, first of all we will discuss about the valencies. Okay. So what is valency? So when we talk about this valency, we can say like this: the chemical behavior of the element is mainly decided by the electron present in its outermost shell, right? So this chemical behavior of the element is mainly decided by what? It is mainly decided by the electron present in its outermost shell, okay, which is also called valence shell, okay, as you know that. Now these electrons, whatever the valence electron which is present in the valence shell, what it will do, it will make bond, or it will participate in the formation of bond, right? And it will or what we can say, it will decide the combining capacity of the element, right? This electron, what it will do, it will participate in the formation of bond and decide the chemical capacity and decide the combining capacity of the element, right? So this combining capacity of the element is called its valency. Okay, I hope you have understood this. So valency is usually what it is, usually a representative element, and is usually equal to number of electrons in the outermost shell. What how many electrons are present in the outermost shell, that will define its valency. Okay, or in some cases we tell like this: in some cases 8 minus the number of electron present in the outermost shell. Just like I will try to give you one example, an example. Suppose we have here lithium, sorry, we have here lithium. Okay, so as we know that lithium, the out in the outermost shell of or we can say the valence electron in lithium is 1, and its valency is also 1, right? Now after that, when we talk about beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So when we see the valency of this, when we talk about the beryllium, it has in number of electron in valence shell of beryllium is 2, okay, and boron is 3, carbon is 4, nitrogen is 5, nitrogen is 5, oxygen is 6, okay, fluorine is 7, and neon is 8. Okay, so these are the number of electrons which is present in the outermost shell of the following elements. Okay, now when we talk about the valency, so in some case the number of electrons present in the outermost shell will be equal to its valency, just like in the case of lithium, valency is 1, here 2, this is 3, and this is 4. Okay, and after this there will be some changes. For nitrogen, the number of electron in the outermost shell is 5, so we will calculate like this: 8 minus 5. Okay, 8 minus 5, which will be 3. Okay, again for oxygen we will count 8 minus 6, which will be 2, right? And for the fluorine we will count 8 minus 7, which will be 1, and for neon 8 minus 8 is equal to 0. So in this way we can find out the valencies. Okay, so I hope you have understood what is valency. And one more thing is there from which we can define this. We can also define like this, that it may be it may also be defined like this, that the number of hydrogen atom, or the number of chlorine atom, or twice the number of oxygen atom that combine with an atom of the given element, with we can also define like this the valency. Okay, so I will give you one example. When we go from lithium to beryllium, on boron to, from lithium, beryllium, boron, carbon, nitrogen, and oxygen. Okay, and after that fluorine. So when we will go like this from left to right, at that time what we will show, that if we are taking the valency with respect to hydrogen, then we will get the same valency. For lithium we will get 1, beryllium 2, boron 3, carbon 4, nitrogen 3, after that nitrogen 3, oxygen 2, and fluorine 1, right? If we are taking this with respect to chlorine, again we will get 1 2 3 4, after that 3 2 1. Okay, I hope you have understood this. Now next is variations. Okay, how this valency so a variation in the periodic table. So when we talk about the variation in period on moving from left to right, when we will move from left to right across the period, okay, across the period, when we will move left to right, the valency with respect to the hydrogen and chlorine will increase from 1 to 4. It will increase from 1 to 4, as I have already told you. It will increase from 1 to 4 and then decreases from 4 to 0. 0 will be forward for novel gases, right? First of all, it will from one moving from left to right across the period, the valency with respect to the hydrogen and chlorine increases from 1 to 4 and then decreases from 4 to 0. Okay, as is evident what as I have already told you how it used to come. Okay, as you can see here, for group 1, 1 2, here you can see 1 2 13 14 15 16 and 17, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. You can see the number of valence electron is 1 2 3 4 5 6 7, and after that 1 2 3 4 3 2 1, right? So in this way there is a variation in period, variation of valency in the period, right? Now after that, when we talk about the group, so we all know that all the elements present in the group possess same number of valence electron, right? So what we can say, on moving down the group, there is no variation in valencies of the element. Okay, why? Because we know that all the elements present in the group show same valency. Okay, for example, you can take uh, all the elements in group 1 have a valency equal to 1, while that of group 2 has a valency of 2. So in variation of valency in periodic table, that does not show any trend. Okay, or we can say it is same. So now this was all about the valencies. I hope you have understood this, and about valency I hope you have also learned in class 10 and 9, right? So now we will discuss about the atomic radii. Okay, so atomic radii, or we can say that the size of atom. Okay, so what is this atomic radii? So for defining, for simple definition, if you want to define, as we know that from the modern periodic table or modern periodic law, or we can say that according to the quantum mechanics model of atom, this atom does not possess a well defined boundary, right? Because the electron cloud surrounding the nucleus extend to infinity. Okay, however, the distance between the nucleus and the point where the electrons density is effectively zero, there may be that may be regarded as the radius of the atom, right? Again, one more thing is there, the boundary of the nucleus is also not well defined. So in this case, what we can do, we can easily define atomic radius as atomic radius, or the size of the atom, may be regarded as the distance from the center of the nucleus, okay, to the outermost cell of the electron, or we can say that to the outermost cell where the probability of finding an electron is maximum. Okay, or we can also define like this: it is a distance from the nucleus to which the outermost electron uh, up to the point at which the probability of finding an electron is maximum. Okay, as we can say like this, suppose this is an atom, this is a nucleus, so what will be the distance? It will be this. Okay, this will be the distance. Or since this line is imaginary, right? This line is an imaginary line, so we can say like this: from the nucleus, whatever the probability of finding an electron is there, suppose the probability of finding an electron is here or here or here, something like this, so the distance will be this. Okay, so this is called atomic radii. I hope you have understood this. So now when we talk about we will discuss this, the variation of atomic radii in period and group in detail. First of all, we know the let me tell you the terms. Okay, now after atomic radii, we have crystal radii, or sometimes you will see atomic radius, or which in some book you will see metallic radius. Okay, so what the this metallic radius or atomic radius or crystal radius is? So it is defined as the half of the internuclear distance separating two adjacent atom in a metallic lattice. Okay, as it is like this. When we talk about the metallic radius, so metallic radius will be like this. One is here and another one is just touching this. Okay, another one is just touching like this. Okay, and this may be, sorry, another one is just touching this one like this. Okay, just touching, not overlapping, it is just touching this. Okay, and suppose this is the nucleus here. Okay, in here the nucleus is here. So what will be the metallic radius? So metallic radius will be the distance from the center. What we will take one distance here, suppose this. Okay, and from here suppose this. Okay, and the distance will be this. Okay, the distance will be this. This will be the metallic radius. Okay, so it is the distance as half of the internuclear distance separating the two adjacent metal atom in a metallic lattice. Okay, so I hope you have understood this, what is this metallic radius is. Okay, so now we will see covalent radius. So when we discuss about the covalent radius, so the term covalent is used to specify the size of an atom which is covalently linked. Okay, I hope you know what is covalent bond, ionic bond, right? So which is covalently linked to some other atom. Okay, or if you want to define this covalent radius, we can define like this. It is defined as one half of the distance between the center of the nucleus of the two similar atom bounded together by a single covalent bond. Okay, so for if we can calculate this. For calculating the covalent radius, let me tell you what is covalent radius. In covalent radius, you have seen in atomic radius the boundary was just touching, right? But in metallic covalent radius, it will overlap just like this. One is here and another one is here. It will overlap like this. Okay, it will overlap like this. Okay, and the distance will be, suppose the distance will be same as we have calculated for that. For that one, we have calculated for that one, distance will be this, from here to here. Okay, after that here, and from here to here. Okay, this will be the distance. And if you want to calculate this, for this, one scientist named Slater, he has given one formula. So for we can use that formula also. So this type of when we discuss about the covalent radius is generally two type. Okay, one is homonuclear diatomic molecules and another one is heteronuclear diatomic molecules. So this is, suppose for homonuclear diatomic molecules, example like Cl2, Cl2. Okay, example like Cl2. Okay, and Br2, or H2 or N2. These are what? These are all homonuclear diatomic molecules, right? So for this, for calculating the homonuclear diatomic molecules radius, we can use this formula. There is a simple formula. Suppose this is the radius, covalent radius. So it will be, suppose this is what we are representing this one as d a d dash daa dash. Okay, da dash a. So it will be d a dash a divided by 2. This is a simple formula from which we can calculate for the covalent radius for homonuclear diatomic molecules. Now for heteroatomic diatomic for heteroatomic, so for heteroatomic we will use different formula. Okay, for the for heteroatomic for heteronuclear, sorry, for heteronuclear diatomic molecules. So just like, for that we can calculate like this. That's the formula. That formula will be, this. Okay, suppose this distance now, this distance, suppose this is an heteronuclear diatomic molecules. So its distance is, suppose this distance is, sorry, this distance is d a dash b. Okay, d a dash b, suppose. Okay, so the formula will be, formula I am writing here, suppose the formula will be like this: d a dash b will be equal to ra plus rb minus 0.09 delta x. Delta x is here what? It is an electronegativity difference. We will discuss what is electronegativity difference. Okay, suppose this one is a and this one is b. To find the covalent radius of heteronuclear diatomic molecules, we will use this formula. Okay, so I hope you have understood what is heteronuclear diatomic molecules. So now next we will study van der Waal radius. So what is this van der Waal radius? So it is also defined as one half of the distance between the nuclei of two atoms of the same substance at their closest approach. Means the closest approach of two atoms means what does it means? That it means that the stage when the atoms are unable to come more closer. Okay, it is a stage when the atoms are unable to come more closer without bond. Okay, without bond formation, or we can also tell like this: at this stage the atoms are in contact with each other without bond formation. Okay, so this is what this is called van der Waal radius. It may be noticed that the covalent radius of an atom is much smaller than that of the van der Waal radius. What is van der Waal radius? Let me draw here so that you can easily understand. Suppose we have two same molecules or same substance. Okay, suppose one is this, one is this. Okay, and it is overlapped by this, like this. Okay, one is this, and here is one atom is here and another one is here, right? So what will be the van der Waal radius? When we are asked to calculate the van der Waal radius, the van der Waal radius will be this. Okay, van der Waal radius will be, suppose this is a midpoint here, central, and his center is here, here, and here. So van der Waal radius will be this. Okay, wait, let me draw a little bit bigger so that you can understand. So the van der Waal radius will be this, generating from here. Okay, here, and suppose it is generating from here. Okay, so the van der Waal radius will be this. Okay, van der Waal radius will be this. I hope you have understood this. So we can, for van der Waal radius, we can also tell like this: it is the sum of the van der Waals radius of two atom is the shortest distance between the two immediately adjacent atom, either of same or different element, in the substance, in the in the structure of the solid compound in which they are bounded to each other. Okay, so always remember that van der Waal radius. Okay, van der Waal van der Waal always remember that the van der Waal radius, if it is denoting by this VDW, it will be always bigger than the radius of the metallic radius. Okay, and it will be bigger than that of the covalent radius. Okay, I hope you have understood what is van der Waal radius, right? Now after this, after discussing this van der Waal radius, we will see the variation. Okay, how these variations of atomic radius used to vary in a periodic table, or we can say that the variation of atomic radius in the periodic table. Now we will see that. Okay, so now first of all we will see here. First of all we will see, yes, period, variation of, you can see here, variation of atomic radius in a period. Okay, so variation of atomic radius in a period, as you can see here. So how we can see that on moving from left to right. Okay, when we are moving from left to right. Okay, when we are moving from left to right, like this, left to right, in the period, the number of cells remain the same, right? Number of cells are not increasing. So if number of cells are not increasing, but due to the increase in the atomic number, when we are going from left to right, there is a number of cells remain the same. Okay, but the increase in the atomic number, the nuclear charge increases progressively, right? So as a result, what will happen, the electron cloud is pulled closer to the nucleus. Okay, and this cause a decrease in the size of the atom. Okay, so hence what we can say, in general, the atomic radius from decreases on moving from left to right in the period. So as you can see, I will try to explain this. When we will see, the now valence number of cells will not increase, right? The number of cells, suppose it will be same, number of cells will be same when we are moving across the period, like this. Number of cells are same, but the number of electrons are in, means the atomic number are increasing, means the nucleus which is present here, suppose the nucleus which is present here, suppose, so it will generate, suppose this force to this, suppose this is the outermost cell, so the force it will generate here. After that, here this one, this will generate here, this will generate here. But as the number of nucleus, atomic number is increasing, the mass of the nucleus is also increasing, right? So if the mass of the nucleus is increasing, the nuclear charge will also increase. And if the nuclear charge is increasing, what it will do, it will pull the electron strongly towards itself. That is why what will happen, this cell will shrink. Okay, what will happen, this cell will shrink like this cell will shrink like this cell will shrink like this. Okay, and that is why the size of the nucleus, and that is why the size of the atom will decrease. Okay, sorry, the atomic radius will decrease. Okay, so I hope you have understood this. So if you have any confusion in nuclear charge, suppose I hope all of you know what is nuclear charge, right? But we can I will explain you what is nuclear charge, because most of you, if you have forgot or something. So nuclear charge is what, it is the outer, if the outer electrons are attracted towards the nucleus by the nuclear charge. Okay, it is the charge on which, suppose we have this is our nucleus, and this is our first orbit, second orbit, third orbit. Okay, in third orbit there is a electron. Okay, like this electron is there. So the force which will exerted by this nucleus, okay, to attract this electron towards itself is called nuclear charge. Okay, I hope you have understood this. Now one more thing is there, screening effect. This thing you have to know is screening effect. Screening effect is what, this is the decrease in the force of attraction exerted by the nucleus on the valence electron due to the inner electron. It is also called shielding effect or screening effect. Let me tell you one thing. What will happen, suppose this is the three cells here. Okay, so at that time what will happen, there is a 3 to 4 electrons is there, right? Suppose the 4 electron is there, 5, 6, 7, 8, suppose. Okay, and here suppose it has 2 electron is there. Okay, and here also, let me draw it again so that I can explain you clearly. Suppose we have this nucleus, first cell 2 electron, second cell 8 electron, after that again 8. Okay, so suppose this is the first cell, 1, two electron. After that, one, two, three, four, five, six, seven, eight. Okay, and here also one, two, three, four, five, six, seven, eight. Okay, this is like this. So what will happen, this nucleus, since it is a nucleus here, this nucleus suppose we are talking about this, so this nucleus will exert some force to this nucleus, to this electron, and with that force this nucleus will try to pull this electron towards itself, right? This nucleus will try to pull the electron towards itself. If it will exert some pressure here, force here, and with that force the nucleus will try to attract this electron towards itself. So between them, what will happen, between this here to here, these electrons are there, right? This one, these electrons are also present there, right? So what these electrons will do, it will shield that nuclear charge. Okay, means what, it this will this electron will, just we can say like this electron will filter the charge, so that there will be a less charge on the nucleus. Means what we have seen, you can tell like this. Suppose uh, there is a water is flowing, okay, and in that water, if we will put one something like clothes or something else, then what will happen, the all the waste particle in that water stop by that close, right? The same thing is happening here. What it will do, these electrons are just building a wall, or we can say like this electrons which is present here, these electrons, this will make a one wall, and from that wall what it will do, it the force which was, suppose at that time when this electron was not shielding, when this electron was not shielding at that time, suppose the force on this electron was suppose 10 newton. Suppose I am just telling, or we can take the energy, not Newton here, but if you are taking that, suppose the 10 kilojoule, okay, 10 joule energy was exerted on that electron. Now what will happen after this electron, with the shielding of this electron, what will happen in this electron will get the attraction force of this electron towards the nucleus will decrease to, suppose it may decrease to 7, 6, 8, like this. I hope you have understood now, right? So this type of effect is called what, shielding effect or screening effect. Okay, this word I will use in later on in this chapter, so keep in mind this. Okay, the decrease in the force of attraction exerted by the nucleus on the valence electron due to the inner electron is called shielding or screening effect. Okay, so I hope you have understood this. Now, after this, we will see variation of atomic radius in a group. So when we talk about the variation of atomic radius in a group, what we can say, on moving down the group, when we are moving down the group, what will happen? The nuclear charge increases with the nuclear charge increases, right, with the atomic number, because atomic number is increasing. When we go down the group, atomic number will increase, right? As you can see here, atomic number is increasing, right, when we are going down the group. So but at the same time, at the same time, what will happen, the number of shell also increases. Okay, so you can say like this, in the first cell if it is 2, then in the next cell it will become 3, right? Like this, in the first cell if it is, wait, suppose in the first cell it is 1, 2, so when we go into the second group, in the down the group, it will, the cell number of cell will also increase, right, because the atomic number is increasing. In the third cell it will become 1, 2, 3, 4, like this, the number of cell will increase, right? So since the number of cell are increasing on moving down the group, the nuclear charge is increasing with the atomic number, but at the same time the number of cells are also increasing. So this take the valence shell further from the nucleus. Okay, this take the, since the number of cells are increasing, then we can say that the distance between the nucleus and the uh, valence cell is also increasing. So this will result in the decrease in the nuclear charge and increase in the size of the atom. Okay, I hope you have understood this, what is happening here. So once again let me explain you. Suppose There is the second. In the second it is 3. Wait. First cell is here, second is here, 3, right? Now next is, suppose this one is 4. I am doing writing here. I am drawing here just because there is no space, right? Like this. So as you can see, the distance between the nucleus and this cell is very less, right? The distance between this nucleus and this cell is this is what, this is the valence shell for this atom. This is a valence shell, so you can see distance is very less. Here the distance is increased, here the distance has more increased, right? So as we are going down the group, the number of cells are increasing, the atomic number is increasing, no doubt, but uh, side by side number of cells are also increasing. So what will happen, as the number of cells are increasing, this will take the valence cell far from the nucleus, okay, and this will result in the effective, and this will result in the decrease of effective nuclear charge and the increase in the size of the atom, okay. So thus what we can conclude, we can conclude that the atomic radius increases on moving down the group, okay. So I hope you have understood this also. So now next is ionic radius, okay. So what is this ionic radius? So I hope all of you know what is ion, what is cation, what is anion, right? In the junior classes we have learned that from a neutral atom, if we are just removing an electron, then it will become cation, and if we are in a neutral atom, if we are giving an electron, it will become anion, right? So what, when we talk about the ionic radius, here it is given, when we talk about the ionic radius, ionic radius, the if we want to define, so we can define like this: the removal of an electron from an atom resulting in the formation of cation, right? Whereas the gain of electron leads to an anion. Thus the ionic radius can be estimated by measuring the distance between the cation and anion in a crystal, okay. It is just nothing but a distance between the cation and an anion in a nucleus, okay. Let me, if yes, it is not given here, so let me draw this, okay. See here, what will be the ionic radius? Same as it is. Let me make it a little bit smaller. Suppose this one, and this one just touching this. As we know, I have drawn this. Smaller one is what, cation, right? And the bigger one is anion, we all know that. And the distance, what will be the distance here? So the distance will be, suppose, from here to suppose this is one distance here, okay. And and from here also we can draw one here, okay, and from here also, like this. So this is what, from here to here, or from here to here, this is what radius of anion, okay. This one, this because this is anion. And from here to here, what is this? This is a radius of cation, right? And now when it, if we are expanding this like this, and if we are expanding this one like this, and if we are, sorry, if we are expanding this one like this, okay, and this one like this, so this distance from here to here, it will become what, internuclear distance, or we can say ionic radius of a cation and anion. I hope you have understood what is the ionic radius of cation and anion. So when we talk about the variation, so ionic radius show a variation similar to those of the atomic radius. As you can see, ionic radius show a variation as those of the similar to the atomic radius, okay. As and thus the ionic radius increases in a group, okay, as we see here. As you can see here, it is increasing, right? You can see here it is increasing. As you can see here, here also it is increasing, okay. So what we can say, ionic radius, then if you talk about the period, ionic radius will decrease in the period. Okay, it can be seen here, as you can see here, ionic radius is decreasing across the period, right? So I hope you have got some idea about this. Now next is ionization enthalpy. Okay, so before ionization enthalpy, I will try to tell you one thing, one compound which is called isoelectric ions. Okay, or isoelectronic ions. So isoelectronic ions means what? ISO. Okay, ELECTRONIC, isoelectronic ions. So what does it means? The ions of different element, okay, ions of different element which possess the same number of electrons are called isoelectronic ions. Okay, and these isoelectric ions possess the same arrangement of electron but differ in the nuclear charge. Okay, for example, we can say, if we are talking about the isoelectronic ions, so we can take the example like P3 minus here, S2 minus here, Cl minus here, K plus here, Ca2 plus here. So these are all isoelectronic ions, right? And each ion contains 18 electrons. Okay, and the nuclear charge of these ions are plus 15 for this, for 16 plus 17 plus 19 and plus 20. Okay, so I hope you have understood this. So this was all about the ionic radius, atomic radius and all. So keep up to this. In the next class we will start ionization enthalpy. Till that, thank you.